and how they enable us to look into some of the mysteries of life and even see how the universe began.
The electron to the 20th century is like the steam engine was to the 19th century. It has defined society, it's defined technology, it is in everything. If you want to know how important the electron has been in the 20th century, come back on the 1st of January 2000. And if the whole world has ground to a halt because of the millennium bug, then you will see how important the electron is, because it's the electron that is driving the whole of modern computer science, modern technology, modern electronics. All of chemistry is electrons on the move. All of life is electrons on the move. Strike a match, what's happening is that electrons are jumping from one atom to another, and the energy released ends up as flame. Breathe in oxygen into your lungs. Electrons on the edge of the oxygen atom merge and change place with electrons in the carbon inside your lungs, turning into carbon dioxide, which you breathe out. It's electrons on the move that make it all work.
The movement of electrons creates light, and the easiest way to make light is to heat something up. A light bulb is simply a thin filament of wire, causing a resistance to the electric current. It heats up to several thousand degrees Celsius and enables electrons on the surface to give out light. Electrons allow us to see the visible world. It's the energy of electrons on the move which creates the light which interacts with the skin of the model's face. Some of the light is absorbed, but some is reflected to reach the eye through the camera lens. The human eye is quite remarkable. It enables us to see fine detail in full color in 3 dimensions. But if we want to go far beyond the limits of the eye, we have to use a microscope. Inside a beehive, there's a whole world in miniature. 50,000 bees each have their own cell to look after, and they have to move about in total darkness. How do they find their way around? The answer is in the tip of the bee's antenna. Under an optical microscope, a lot of hidden detail can be seen. The bee has delicate little brushes on its forelegs, with which it keeps the antennae clean. But even with the most powerful optical microscope, there's a limit to how much we can see. Light travels in waves. If the waves come up against a large object, they're reflected and can be seen by the eye. But if the object is tiny, they flow straight on past. The light waves are larger than the obstacle, and so none get reflected. So if we want to see the individual sensors on the tip of the bee's antenna, we have to put the head of the bee into an electron microscope. We can now see that the bee has thousands of fine sensors that respond to heat and smell and which tell it exactly where it is in the hive. This image is being magnified over 100,000 times. Electrons, being much smaller than light waves, can be fired in a narrow beam against the tiniest object. They'll bounce off it and they can be picked up and fed into a TV system.
We're now going to use the TV as an electron microscope. Now, the idea here is that you can scan your electron beam, as we've seen in Bryson's demonstrations, across things. You can make them glow, or there may be a shadow left behind, bright spots and dark spots. You can then send that information across to a television screen, which can reproduce the bright and dark as an image. And we're going to show you this with a little demonstration. First of all, over here, Rebecca is going to assist me with this. She's going to play the role of the electron beam that will scan across an image here. We can then send that electrical information across to a screen where Bryson will demonstrate it to us.
This board then represents our television set. And the signal of bright and dark regions is used to control how much electricity flows in the electron beam, and therefore the distribution of light and dark patches on this screen.
And what we will do in a moment is that Rebecca will scan her electron beam across here in time with this clock, and the same clock on the other side will give Bryson the cue for his response over there. And if we're lucky, we should get something very interesting. 3, 2, 1, go. What have we got?
Not bad if I say so myself.
Not bad.
Well, I have to say that's the best we've done so far. It's not perfect, but then again, Rebecca and I are not automata, we're not machines. But a modern electron microscope and television can produce not 10 lines, as we have here, but very easily can produce 1,000 lines. At the moment, the sample that Rebecca was scanning and the television screen are the same size. But there's no need for that. It's very simple to make an electron microscope scan an area of about 1 centimetre with a beam 1,000 times finer than that.
So, this simple demonstration shows you something quite remarkable. The electron microscope is giving us 2 things for the price of 1. First of all, it's using electrons, which means that it enables you to see things in a way that your eyes could never do, because your eyes respond to light. The second thing is that you don't need any moving mirrors, you don't need any special optical lenses. It's the electrons being manipulated that do it all for you. Now, this might seem like too good to be true, but in fact it works, and Bryson is going to show us the real thing.
Well, recently I had the opportunity to go to the laboratories of a company called JEOL, who manufacture electron microscopes, amongst other things, and record these images. You see on the screen here what looks like a lot of hairs, and indeed they are, but at the bottom of the image you may just be able to see a very thin white line. That line is showing you a distance of 1/100th of a millimetre. So those hairs are incredibly fine, and as we scan the beam over a larger and larger area, the magnification is reduced, and you see that we're not looking at human hairs, but hairs on the wing of an insect. And as we change the area of the sample that we scan our beam over, you see that the insect is in fact a common or garden wasp. Now, the wing of the wasp was a very beautiful structure, but it's the other end of the wasp that normally interests us, so we can move our beam down and concentrate on the sting. Now that we're lined up, we can zoom in, scan over a very much smaller area, and we're producing enormous magnifications again. Now, when I was young, I was always told that there was a difference between a bee sting and a wasp sting. A bee sting has got barbs on it. It's designed to sting you once and remain within your flesh when the bee has stung you. But a wasp sting is designed to sting many, many times, and as such is very smooth. But I think you'll already be able to see with our scale bar at the bottom, again showing 1/100th of a millimetre, that a wasp sting, in fact, does have barbs. Those barbs are, in fact, quite significant. I mean, they're designed to cut and tear the flesh to allow the venom to be injected. Now, the signal from an electron microscope is intrinsically electrical. And as such, it's very simple to put that into a computer and say to the computer, don't show me every picture, but look at 100 pictures, add them together, and then show me the result. And you can see that process occurring from the top of the screen. And when we do that averaging, you can see the stunning quality of images that we can create. Look at how smooth the wasp sting is. Look at how sharp those barbs are. And you can see that the tip of the wasp sting is about 1/100th of a millimetre across. It's really not at all surprising that it's able to pierce your skin. You may also just be able to see the remains of the last thing that the wasp stung left on the tip of the wasp. It was in fact a bee from the beehive that it was attacking. Now, electron microscopes are incredibly simple to operate these days. If you can use one of these modern electronic gadgets, a Game Boy, then I could teach you to operate a machine like this in an afternoon. And you can produce stunning images like that. And I think it's quite a testament to the development of electronic engineers that we've progressed from a research tool to an everyday tool in the laboratory in just 20 or 30 years.
Scientist Eileen Cox is researching into the life of a mysterious and little-known organism called a diatom. Diatoms consist of a single cell which grow an outer shell. It's the characteristics of the shell that tells them apart, and these can only be seen under an electron microscope.
Well, this one would be found in very well aerated habitats. It likes lots of dissolved oxygen. This one in particular was growing on the bottom of some duckweed, which is the smallest flowering plant and floats on water. It was actually in a ditch, but it's quite a healthy sort of habitat, but with lots of dissolved nutrients. This particular cell is in fact only the hundredth of a millimetre across, so it's about a 20th of a millimetre long. So they're very, very tiny. You would never see anything like this with a naked eye unless you had hundreds together, close together, and then they'd appear as a sort of brownish coating. So the brownish coatings you see on stones or on the slimy feel on some pondweeds are due to diatoms very often. They're happily growing on those surfaces, photosynthesizing, and acting as food for some of the small animals that grow in fresh water. Diatoms are extremely important for the functioning of any aquatic system. So in any body of water, they're very likely to occur, growing, producing oxygen, and acting as food for animals. But because different species occur under different conditions, they also can tell us about the water chemistry and about the health of an aquatic system as a whole. And for example, if you get poisons released into a river system, they'll very quickly kill many of the diatoms or all the diatoms. So if you find a large number of dead diatoms, you know there's been a very detrimental effect on that system.
The Natural History Museum is one of the most advanced centres for the study and classification of plants and animals. Scientists here catalogue species sent to them from all over the world. One of their jobs is to help conserve sites of scientific interest and protect endangered species. This involves carrying out detailed environmental studies of forests, coasts and rivers. So what has Eileen Cox learnt from the diatom about the Thames?
I think it's reasonable. I wouldn't want to drink it. But it's certainly a lot cleaner than it used to be. And it's supporting a good range of algae and of macroinvertebrates, and the fish are coming back.
Diatoms are among the world's oldest organisms and probably go back to the very dawn of evolution. Now the electron is opening up secrets even older than the diatom. How the universe itself began. The Big Bang, a colossal explosion of energy 15 billion years ago. The birth of all matter, the galaxies, the stars, the Earth. All forms of life had their beginnings in this burst of energy.
One of the most exciting questions in science right now is, how did the universe begin? How did the atoms that make everything first get formed? Well, that's the sort of question that we're trying to answer here at CERN, the European Particle Physics Centre in Geneva, where I work.
To try and provide answers to this tantalizing question, they've built the world's largest particle accelerator between Lake Geneva and the Jura Mountains, 100 meters underground.
We don't know why the Big Bang happens. what we can do in science is go back nearer and nearer to the Big Bang. Today at CERN, we are able to get back to within less than a billionth of a second after the Big Bang. But that's pretty near. It's 27 kilometers all the way around the tunnel. It'll take me on the bike about an hour and a half to get round. But the electrons inside this tube, they go all the way around 11,000 times every second.
Travelling in a total vacuum, the electrons are guided around the tunnel by thousands of electromagnets. Like an enormous slingshot, electrons and positrons are whirled around in opposite directions at the speed of light. Accelerating cavities pump the necessary energy into the particles which finally collide head-on, annihilating each other and creating a mini Big Bang.
There's 4 places around the ring where we bring the beams together, and that's really where the action is, and we're going to see one of them right now. It's right beneath my feet so that we can recreate the intense heat of the Big Bang over and over again and see what happens. The results are sent to computer screens all over the world.
The Internet, or World Wide Web, was first developed at the Centre for Particle Research here in Geneva, so that scientists in many countries could help interpret the results. These are the tracks left by particles and their antiparticles, and from the way they curve, their momentum and their charge, scientists can tell what they are. They've proved or disproved theories that have existed since the 1920s about the makeup of the atom, and they've made new discoveries about subatomic particles.
We've come a long way in 100 years. 100 years ago, the electron was discovered by J.J. Thomson in this little tube. Today, the electron's being used as a tool to answer big questions like, where did the universe come from? And this is the scale of the enterprise. Just compare that with how it all began.
So, what's going to be discovered next? I don't know. That's for you to find out. The great adventure goes on. I just would love to be able to come back in 100 years' time and see the things that they would be taking for granted that we regard as miracles now, or haven't even thought of. After all, go back 100 years, and let's just close the show by reminding ourselves, would Thomson even ever have thought it would lead to this?